Hey yo, what's up guys? My name is Devin, my YouTube channel is DRG Bros, and today you're going to be talking about, it's kind of Diophanic? I think that's how you say it, Diophanic Equations. So basically, if you'll recall from our last video, given any equation ax squared plus bx plus c, we can solve for x by using the quadratic formula. So x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So can we do this for cubic equations? Yes, we can. At least for special cases, without getting too complicated. So we have so we can use this equation as an example. We have x to the 6th minus 5x cubed plus 6 equals 0. So we let a equal x cubed, and then we plug it in. So we split the x to the 6th. We have x cubed squared minus 5x cubed plus 6 equals 0. So we have a squared minus 5a plus 6 equals 0. So a minus 3, a minus 2 equals 0. So a minus 3 equals 0 or a minus 2 equals 0. We're going to plug it back in and we're going to swap it. So we have x cubed equals 3 or x cubed equals 2. Cube root everything, like so. And you'll find that we're left with x equals the cube root of 3, the cube root of 2. But as I mentioned, we only have two solutions though right here, right? But according to the degree of the polynomial, there's supposed to be 6 solutions. What are the other solutions? Well, they're complex numbers. They're not real. They're not real numbers, but they're complex. They're imaginary numbers. And so for that reason, we're not going to go into too much detail on how to solve it here. So now we're going to move on, and we're going to get into the video. So now we have Diophanic equations. So basically, Diophanic equations are a class of problems named after Diophantus of Alexandria around 250 AD. He wrote a famous book called Arithmetica, which is basically arithmetic. So yeah. So there's a Library of Alexandria. It's a famous university that was founded to honor Aristotle, Plato, and Socrates. That was basically known for the book. So now, basically, what the equations are, we're given a set of things. So we have 2x plus 3y equals 8, for example. And we have to find two integer values of x and y that make the statement true. So, for instance, I'm going to write 2 of them. I want to see if you can come up with 2 of your own. So, I know there's at least 4 answers to this. Now, technically, there should be an infinite number of solutions. Maybe not, actually. Actually, I don't think so. So, yeah, let me give you some. So, we have 1 and 2, because 2 plus 6 equals 8. We have negative 2 and 4, because negative 4 plus 12 is 8. I'm going to give you a moment right now, pause the video, and try to come up with at least 2 more answers. Alright, so you may have not gotten the same 2 I did, but for another 2 sets of answers, I got negative 5 and 6, because 18 minus 10 is 8. And 4 and 0, because 8 plus 0 is 8. If the one I got wasn't one of those 4, still probably correct. Let's do another one. So we have 4x plus 3y equals 1. Okay? So there's not a lot of solutions to this one, at least that I found. But to the two I found for sure, there's 1 and -1, because 4 minus 3 equals 1. And I also got 4 and -5. 16 minus 15 equals 1. So let's do one more. So we have 2x plus 4y equals 1. So this one, pause the video, try to figure out a solution for yourself. Alright, so, as it turns out, this equation has no solutions. Now, here's why. There's 2 reasons why here. So first off, they have to be integers. But there's a rule. Basically, if there's 2 even numbers, or if even one of them is even, look, an odd times an odd is odd. So we have 1 times 3 is odd. If we have an odd times an even, let's say 3 times 2, it's always going to be an even number. And if it's an even times an even, it's going to be an even number. So no matter what we do, since both of these are even, there is no possible way for us to get a value that's 1. Here's another way to check it. We move the 2x to the other side, so we have 4y equals -2x plus 1. Divide everything by 4, and we have -1/2 x plus 1/4. So that, like, yeah, we need an integer to solve this equation. So, but the problems we just solved are called linear Diophanatic equations in the form ax plus by equals c. I don't know why I wrote a 3 there. So now we're going to move on to our last concept of the video. We're going to be applying this to a real-world example. We're going to be using Pythagorean triples. So basically, given any right triangle, see, we had a right triangle, where C is the hypotenuse and A and B are the side lengths, we can find the side lengths. So we know that A, B, and C can't be random, but they have to satisfy the Pythagorean theorem. A squared plus B squared equals C squared. Okay? So to find integer solutions, so first we're going to come up with a generating formula we can use. So we're going to let A be equal to m squared minus n squared, B be equal to 2mn, and C be equal to m squared plus n squared. So now what we're going to do is we are going to solve. So we have so we're going to have m squared plus n squared squared in parentheses plus parentheses 2mn squared equals m squared plus n squared squared. So I know I put a plus here, but this is actually a minus in the front because we're plugging it in. I don't know how I messed it up. So now we're going to square it, and instead of multiplying it right in, we're just going to square it out. It's going to m squared minus n squared, m squared minus n squared. The 2mn, we're just going to go ahead and just fully do it. So we have 4m squared n squared equals sorry, m squared minus n squared, or plus m squared plus n squared. So now we can multiply these two. So we get m to the 4th minus minus m squared n squared minus n squared m squared plus n to the 4th plus 4m squared n squared equals m to the 4th plus m squared n squared plus n squared m squared plus n to the 4th. We can simplify this down slightly. So we have m to the fourth minus 2m squared n squared plus n to the fourth plus 4m squared n squared equals m to the fourth plus 2m squared n squared plus n to the fourth. So then we get our, and then we add the n squared, so we have m to the fourth plus 2m squared n squared plus n squared, or n to the fourth, equals m to the fourth plus 2m squared n squared plus n to the fourth. And you can see now that these match. So we found something. So for any given triangle, if we write A as m squared plus, or n squared minus n squared, B as 2mn, and C as m squared plus n squared, we're always going to get a Pythagorean triple. So for any value, I'm just going to make a little table here, A, B, and C. So if m was 2 and n was 1, then that would make A 3, B 4, and C 5, which is a Pythagorean triple. If m was 3 and n was 1, A would be 8, B would be 6, and C would be 10. Again, being a Pythagorean triple. The last one, probably the most famous, aside from maybe 3, 4, 5. If m is 3 and n is 2, then we have 5, 12, and 13. Now, this also shows that there's an infinite number of solutions, because, as you know, there's an infinite number of integers. So, if there's an infinite number of integers, then there's an infinite number of m's and n's. And if there's an infinite number of m's and n's, then there's infinite a, b, and c. So there's an infinite number of Pythagorean triples. Thank you all very much for watching this video. I hope you enjoy. Please like and subscribe and go check out some of our other content. Bye, guys.